Hello and welcome to our channel Artezmia for another video about electronics. In this episode we will take our working laser tripwire alarm that sends a message to our smartphone when triggered, and we will replace the WeMOS D1 Mini microcontroller with an ESP32-S2 Mini, an ESP32-C3 Mini, and an ESP32-C3 Pico. Three boards that are pin compatible with the D1 Mini. The advantage of these boards is that we can program them with the Esp-Idf framework that we showed in our last videos how to install on the Linux computer running a Debian-based distribution that can be pure Debian, Ubuntu, Mint, Devrant, Sparky Linux. There are many flavors. In this video, we will assume you're working with Esp-Idf, whether on Linux or not. There shouldn't be much difference if you're on Windows or Mac and you know what you're doing. Even though your understanding of what we're doing will be much better if you watched all our previous videos, it is not absolutely necessary, and I will make this a standalone video. Sorry for those of you who watched all of our previous videos. There will be some repeated material from the previous videos, but I will try to reduce it as much as possible. As usual, the code, the drawing, and the bill of materials will be available at my webpage. The address is in the first comment below the description. We have a small board with two laser modules powered with 5 volts through a micro USB port and an old phone charger. On another board, we have two light-dependent resistors, SDRs, in series that will receive the laser beams. When both beams are interrupted at the same time, this triggers an alarm that will sound a certain length of time, flashes pseudo-random strobe lights, and sends a message to your smartphone via the Telegram app that the alarm was triggered. The two laser beams will be reflected by mirrors in order to focus on the LDRs and be approximately 2 feet apart, vertically spaced. We use two laser beams in series in order to avoid false alarms as much as possible. A pet or a raccoon won't break the two beams at the same time, but a burglar will have a hard time avoiding it. Here's the bill of materials. We are using an SMD, surface-mounted device, P-channel MOSFET, because the one we chose is much closer to the voltage and current we have in our circuit than any P-channel MOSFET through hole. We soldered our MOSFET on an adapter board SOT23 to P10. We placed the pins on a breadboard, the adapter on top, and we soldered the pins. We soldered the pins after having soldered the MOSFET to the adapter. If you wish, you can use a through-hole P-channel MOSFET if you can find one that will be conducting at -2 volts. My SMD is conducting as 0.45 volts. The principle of the alarm is the following. When both beams are interrupted, the sum of the resistance of the LDRs becomes high, which triggers the 555 timer for a duration T equals 1.1 times R times C, T being in seconds, R in ohms, and C in farads. I chose to use a trim pot instead of a simple resistor, so I can change this duration as needed after the circuit is built. For R equals 1 megohm, C equals 100 microfarads, you get a duration of 110 seconds, which is 1 minute and 50 seconds. The 555 timer is powered with 12 volts to pin 4 and 8. Pin 5 goes to ground through a 10 nanofarad ceramics capacitor. Pin 1 goes to ground directly. Pin 6 and 7 are shorted. Pin 6 connects between the potentiometer that goes to 12 volts and the capacitor electrolytic one that goes to ground. Pin 2 goes between the LDRs and a 20k resistor. The LDRs go to 12 volt and the resistor to ground. Pin 3 connects between two resistors, a 10k ohms that goes to ground and a 100 ohm that connects to the gate of a 2N7000 N-channel MOSFET. The drain of that MOSFET connects to the gate of the P-channel MOSFET, and the source connects to ground. ground. Looking at the P-channel MOSFET now, the gate connects to the drain of the N-channel MOSFET, the 2N7000, and also to the 12-volt rail through a 10K resistor. The logic is the following. When the alarm is triggered, pin 3 goes high, that is, has a non-zero voltage that makes the 2N7000 conducting, and that connects the gate of the P-channel MOSFET to ground, and that makes it conducting between source and drain. For the P-channel, source connects to 12 volt, drain connects to the positive side of the siren, the negative side of the siren going to ground, and the input side of a buck converter that will convert whatever comes out of the drain to 5 volts. The 5 volts will power our microcontroller and the relay module. When the microcontroller is powered up, it sends signals to the relay modules through a logic level converter, and the relay will flash 2 strobe lights according to what is programmed in the microcontroller. The GPIO pins of the microcontroller give only 3.3 volts. That is why we need a logic level converter, LLC, to raise it to 5 volt to signal the relay module. This is explained in more details in videos number 4 and 5. When I first looked at microcontrollers to use in this laser tripwire alarm project, I chose the WeMOS D1 Mini for having a very small footprint, and I used VS Code with Arduino framework. I saw what bad coding I was able to get away with, so I researched the Esp-Idf framework. Unfortunately, the D1 Mini is not supported. Then I tried to find boards that would be pin compatible with the D1 Mini and supported by the Esp-Idf. I found 3 of them: the ESP32-S2 Mini, the ESP32C3 Mini, and the ESP32C3 Pico. So I bought a few of each, and the S2 Mini was the first one I received, so I started working on that one. I installed the Esp-Idf on my computer and started coding. Then about 3 weeks ago, the version 5 of Esp-Idf was published, and my code that worked perfectly fine on 4.3.3 was not working anymore on 5. That's why I made the videos 6 and 7 about installing 5.0 on a Linux computer running Debian, and wrote an example that would work on 5.0. Now I've figured out how to make my code for the alarm work on 5.0, and you can copy the code from my webpage as shown in the first comments. After most of the video was recorded and edited, I found a P-channel MOSFET through hole that might fit the bill, the FQP47P06. The datasheet states that the threshold for becoming conductor is minimum -2 volts and maximum -4 volts. I tried it on the breadboard circuit, and here are the results. The gate source voltage is -2.3 volts, in absolute value above the minimum voltage that the datasheet states, but in the low side of the range, and we don't get the full 12 volts at the drain like with our SMD MOSFET, and the energy is lost in heats. This should be no big deal because the alarm is not triggered all the time, and it's a very little amount of heat. But what's more concerning is that the MOSFET, the FQP47P06 MOSFET, is neither not conducting or totally conducting. It's in between, and we could have some strange effects happening. Plus, we have no clue of what might happen during the powering up of the MCU. We would have to measure voltages with more precision, like with an oscilloscope, for example. Now we are going to talk about the code for our program. So we have a folder called Newtel. In this folder, we have a cmakelist.txt file and a main subdirectory. So the cmakelist.txt file has what is required. This mentions the required minimum CMake version, which is 3.16 as required by Esp-Idf 5.0, even though we probably have 3.50 installed in our system. Now, the extra component directory that's needed is from the Esp-Idf installation directory tree, examples, common components, and the protocol examples common. and we have to define the name of our project within this, which in this case is newtel. Now in the main subdirectory we have three files. We have another cmakelists.txt, which is different from the previous one. We have newtel.c, which in many cases is called main.c, and we have the PEM file for Telegram. That's the certificate for the Telegram, so that we can send a Telegram message and connect to the Telegram server with the proper certificate. This certificate is good until 12/31/2037, so you can use it without any fear. And some other time I'll show how to get this certificate. Okay, the cmakelists.txt file just defines what the our main.c file is. In this case we call it newtel.c. It include directories. Well, we have none, but we might as well put it. We have to embed the txt file, this certificate for Telegram, and so that's why it's important to put the Telegram certificate in this subdirectory. And component compile options, this is something that has become necessary with the Esp-Idf 5.0 version. In previous versions you didn't need this compile options, but building will fail if you don't have this. Okay, now I'm going to talk about the main code. Okay, now we added the rom/gpio.h in this inclusion of libraries. Actually, its place should rather be within the driver/gpio.h, but this was something that was also new in version 5.0 of the ESP-Idf, and I prefer to add it in all my project files, because if I update to any newer version from 5.0, then the driver/gpio.h will be written over, and I will lose this, and I will probably forget to add it again. ESP random.h, this is a library for pseudo-random flashing of the LEDs, so pseudo-random number generation that we will need in our program, because we have pseudo-random flashing LEDs is the alarm is triggered. Now here is what your actual SSID is, and your SS password and your Wi-Fi password is. Maximum number of retry to connect to the access point, 10 works for me. I would rather have a static IP than an IP given by DHCP. If you have quite a few boards on your network, then if one stops working, if it's all with the DHCP, every time you restart your system, or you add a board and then restart the system, you might not know which board has which IP. This one, you perfectly know it. The DNS server, and well, this is pretty much standard. Now I use 5 tags for for error messages and for communicating with the board to be able to. This is just a help for debugging. You need a chat ID that you get when you define the bot on the Telegram messenger. You can check how to do that on the internet. I'm not going to include this in this video. Maybe I might do a video on this some other time. These two lines are to this function, and the few following functions come from the fixed IP and the HTTP client example, and that comes with the Esp-Idf installation. You'd rather take parts of these examples for your code rather than look for code on the internet that might do what you want in the previous versions but will break in 5.0. This especially this one for the HTTP event handler is really broken if you use old code. This is a function to initiate Wi-Fi as a station as opposed to an access point. Now this is what is specific to Telegram. Now these are two functions we define to flash the LEDs pseudo randomly. So we have a ESP random is a random number generator from the ESP, and this will return the length of time it will be flashed. We use two task functions to have the two LEDs blinking independent from one another. We could combine the two in a single one if we would want a flip-flop style, one on, one off, and vice versa. Now this is the app main function, and you can see it has pretty much nothing in it. It just has two calls to the flashing functions, and it has some error checking number to see if we can get a fixed IP when we connect to Wi-Fi. Then it connects to Wi-Fi and sends a message to the log, and this is just calling the Wi-Fi. Okay, this function just tells your board to send a message to Telegram, to your Telegram account. The message here was alarm triggered in the attic. So whenever your alarm goes on, then your ESP32 board will be powered up, and then it will send the signals to flash the LEDs and send this message to your Telegram account. So you can actually change this to whatever you want. Okay, now we're going to build our code and flash it to our board. So we go to the new tel subdirectory as stated before. We have to make sure terminal window is enabled to use the Esp-Idf by running this. Now we have to define which board we're going to use. In this case, it's the ESP32-S2. Now we're going to build the program. We are now ready to flash our ESP32-S2 Mini. We just have to figure out at what port it's plugged in. with the, okay, well, it didn't find it. Why didn't find it? Because it is not in automatic flashing mode. Different from the ESP32C3s, in the ESP32s, this board needs to be put in upload mode. So you just press the O button and then you press the reset button and release it, and then you release the O button. And there you should find your board. Okay, now we have it as USB ACM device TTY ACM 0. So now we are going to be able to flash it. So -p/dev/TTY ACM 0 flash. Okay, it's flashing all right. And now we have an error. So what this error message is all about, it is the ESP32-S2 mini is not self-resetting, so it's still in flashing mode. So we have to reset it, and that's done either by pressing the reset button if you want to keep working with your ESP32 plugged into the computer, or if you just unplug it and plug it to whatever source of power you have and that is ready to go, then it will, upon reloading. To prove this point to you, I will just go through the same exercise with a C3 mini board that's also a Type C board. So for that, I will go back up in the directory tree, and I'll just send the build folder in the SDK config file to trash. And you can see that nothing has moved in the Newtel subdirectory. Now I will show you by running the dmessage pipe to tail that I disconnected the S2 mini board. You see the last line here says USB disconnect. Now I have to define the new board. So instead of a ESP32-S2, it will be an ESP32C3. Whether it's a C3, C3 Mini, C3 Pico, or any kind, it's always a C3. I will build it. Whoops. Oh, okay. What's this all about? Well, I forgot one thing. I forgot that for the C3s, the number of the GPIOs for flashing the LEDs is different than from the S2 mini, and so I have to go here and edit the Newtel.c. I have to go to the end of the functions, and here it is. Here I have to change the numbers 33 and 35 that were for the S2. I have to change this to 8 and and 10. Now save. Okay, I can close this. I'll have to go back to my up my directory tree and delete the build and SDK config. Move them to trash. Okay. Now I have to define the board again. I have to build. And now you see it's built okay, so that was the problem. Now I'm going to see if my board, I'm going to plug my board into a USB port of the computer, and I'm going to see what port it's at. And you can see now I have a new USB device connected. It is with the same port, TTY ACM0, so I can flash it, and you can see it flashes okay. And you can see it's self-resetting. The last line here, last lines say leaving, hard resetting via RTS pin done. So your board is already working. Now if you want it in a separate setting, then not plugged into your computer, well, you can just unplug it and plug it again. It'll work right there. On our board, we included a 0.1 ohm resistor between the positive output pin of the buck converter and the 3.3 volt pin of the microcontroller. The idea was to measure the voltage, hence the current going into the microcontroller. 0.1 ohm will not cause a significant voltage drop when powering up the MCU. More than an exact measurement of current, we wanted to compare the different microcontrollers' power consumption after stabilization. We were really surprised to see that the S2 Mini, C3 Mini, and C3 Pico consume about the same, within 2 milliamps of one another at about 80 milliamps. The D1 Mini consumes significantly less, but the difference in software makes the comparison rather meaningless. Here's a video of my cell phone receiving the message that an alarm was triggered. We can hear in the background the relays being activated. The siren obviously was not connected. If you liked the content of our video, or if you found it even remotely useful, please hit the like button and subscribe to our channel. See you soon for our next episode.